AIS signals. Those signals ships use to try to not run into each other. They're a digital signal and constructed with many of the basics for digital signals. Let's have a look. The purpose of this video is to explain the AIS signal itself. In other words, how to demodulate and how to decode those transmissions. The purpose of this video is not to explain the AIS system as a whole. For that, there is a YouTube video to which I put a link in the description that does a much better job of explaining it than I ever could. Most of the details that I use to demodulate and decode these signals I got from the ITU-R recommendation, ITU-R M1371-5. This is an older recommendation. It turns out that there's actually a newer one, 1371-6. I strongly recommend that you use, if you're going to be doing this yourself, you use the -6. Why? Because between -5 and -6, somebody from the humanities actually got their hands on the manual and said, yeah, let's actually write this so actual human beings can understand it. The 1371-6 is much more understandable than the -5. Honestly, it would have been much easier for me if I'd had access to that -6. It did not come out until February of this year, and I've actually been working on this for a couple of years now. Regardless, I put a link in the description to this recommendation. Feel free to download it and read it at your leisure. In order to have signals to analyze, you have to capture them first. The setup that I use for most of the signals that I have in my inventory, you can see right here on your screen. I have a basic dipole antenna. It's just one of those simple ones that came with one of the RTL SDRs that I ordered years ago. Going into an RTL SDR, in this particular case, this is a Newelec RTL SDR. And then it is going into my laptop. Laptop is running GNU Radio Companion. The reason that I'm using GNU Radio Companion is it allows me to sample at a high sample rate. Sampling at high sample rates is better for sensitivity. It also allows me to do filtering such that I can then lower the sample rate for storing it. In this particular case, I ended up running at 2.4 megahertz sample rate, and then I downsampled to 240 kilohertz. The one thing that you need for collection of AIS signals is proximity to water. When I collected the signals at Fort Smallwood State Park is actually located just south of Baltimore. That gives me access to the Chesapeake Bay traffic going in and out of Baltimore, as well as signals that are continuing further up north. When I collected the AIS signals, I had my RTL SDR centered at 162 megs exactly. The reason being is that the main AIS signal frequencies are 161.975 and 162.025. In other words, 162 megahertz plus and minus 25 kilohertz. Now that I have my file with my AIS signal, the next part is I want to be able to separate the two frequencies and record them into their own files. To do that, I created this flow graph that takes the input file here as a file source. I run it through a throttle just because I want to be able to demonstrate it. Each one of the two signals is going to be separated using a frequency translating FFT filter. The reason that I'm using this particular block is not just because I want to be able to do the frequency translation, meaning I want to be able to take both of those signals, which is now plus and minus 25 kilohertz from the center. I want to be able to set both of them to 0, but I also want to use a specific filter. The specific filter that I want to use is the Gaussian filter, and these are the particular values that I used. When you're using the Gaussian filter in GNU Radio, the specific values refer to the first value is the gain, which is pretty much everybody always sets that to 1. The next value is the number of samples per symbol. In this particular case, if you look at the specification for AIS, it's a bit rate of 9600 kilohertz or 9600 hertz, 9.6 kilohertz. I have a sample rate of 240 kilohertz. If you do the math, if you take 240 kilohertz divided by 9600 hertz, you end up with 25. Hence, that's going to be 25. The next part is the specification very nicely suggests that you use a BT value for the Gaussian filter of 0.5. Hence, I put in 0.5. That's the BT value. The last part is how many taps do you want to have in the filter? Don't ask me where this comes from, but I noticed that a lot of people will tend to use 11 times the number of samples per symbol. Can I explain why that is? No, I cannot. It works, therefore that's what I'm going to use. 11 times 25, and then just to make certain that the system understands that integer, I wrap it with in parentheses and put int in front of it. So the whole thing is firdes.Gaussian, and then in parentheses 1, comma, 25 samples per symbol, comma, 0.5, which is my BT value, my bandwidth time product value, comma, and then int in parentheses 11 times 25. Next, I'm going to set the filter to go into a WAV file sync. Why a WAV file sync? Two reasons. One, it lowers the amount of data that I have to store, and two, Universal Radio Hacker works just fine with it. I've opened Universal Radio Hacker. I'm now going to import one of those two streams that I just created, specifically the one at 161.975 megahertz that I collected at Fort Smallwood. When you first look at it, if I blow this up a little bit, you can see all these spikes. Each one of those spikes corresponds to an AIS transmission. And you'll notice that some of them are larger, some of them are smaller. Obviously, the smaller ones are most likely further away. Larger ones are going to be closer, and so on. What I'm going to do here is I'm going to pick one of these signals, and I'm going to use it for further processing. I'm just going to actually select a slew of them here. I'm going to say create new one from that. I can close this part here. That way I don't have that huge file taking up my resources, but I have several signals here. One of the things I want to show you while we're here is I'm going to open this up into the spectrogram view, and notice that the blue is where it's been filtered, and the pink is the part that's the signal's been allowed to go through. If you've worked with Universal Radio Hacker, you probably know that you can do filtering inside of Universal Radio Hacker. You might be wondering, why did I not just do the filtering in here? Why did I do it in GNU Radio Companion? The big reason is that the filtering in GNU Radio Companion gives me access to the Gaussian filter. You don't have access to that in the Universal Radio Hacker. You have just access to a standard windowed sync filter. I want a Gaussian filter that's a matched filter that gives you slightly better performance than what you're going to get with just a standard windowed sync filter. If you're using Universal Radio Hacker and you really just want to use the filter in here, will it still work? Absolutely it will. Again, you're just going to get slightly better performance with an actual Gaussian filter than as opposed to what you have inside of here. The other thing that Universal Radio Hacker doesn't allow you to do is it does not allow you to set the frequency to shift it to 0. Without that shift, if you have it either 25 kilohertz offset above or below 0, it's going to turn into a DC offset when you go into the demodulated view. Again, it's just a little bit, it's just another step that you have to remember to do, just a little bit more of a pain. Since I was doing the filtering in GNU Radio Companion, why not just go ahead and do the frequency shift, make it to 0, and everything's good. With that, I'm going to pick one of these. I'm just going to say, let's say, for example, this one right here. I'm just going to go ahead and say, let me crop to that particular signal so that now I have just this signal. I'm going to go through my various settings here. First, the noise. The noise is this pink part here. I want to get it a little bit closer to the actual noise level, which is this part down here. It's 0.224 or 0.0224. I'm going to say 0.01. That's a little bit better. The samples per symbol. Remember I calculated before that because I have a sample rate of 240 kilohertz and a 9600 hertz symbol rate, my samples per symbol is 25. I can go ahead and set that, but let's say I didn't know that. Let me come back here and say pretend I didn't know that. I'm going to come under here under demodulated view, and we can see my signal here. And you see these impulses, these shorter impulses. The shortness is due to the Gaussian filtering. It's a consequence of the Gaussian filtering. But I'm going to take one of these shorter impulses and I'm going to click and drag in between these pulses, and look, it says 25, just what we calculated. So I'm going to set that to 25. Error tolerance, I'm going to go ahead and leave that at 5. Modulation is FSK. The modulation is actually Gaussian minimum shift keyed. The Gaussian part's actually not part of the modulation. That's the filtering, that Gaussian filtering that it uses. It's the reason why these impulses look nice and smooth and rounded off. The minimum shift keyed is actually a form of FSK in which your modulation index, that's the ratio between your symbol rate and how much the carrier deviates off of the center frequency when you're doing frequency modulation. Specifically, MSK means that you have a modulation index value of 0.5. Therefore, I'm just going to set it to FSK, and the last thing I want to do while I'm in here is set the center value. And I'm going to look at this, just kind of eyeball it and say I want to make certain that in between the peaks of these short symbols here, that's where I'm setting this line here. This Universal Radio Hacker is going to say that anything in the pink is a 1, anything in the green is a 0. That's where we're going to start. Next, let's go ahead and go into analysis mode. Before we get deep into the decoding in the analysis mode of Universal Radio Hacker, let me just point out, for those of you who don't have access to water and ships with AIS transmitters, I have a link in the description below for my GitHub. On my GitHub, I have created a zip file. Inside of that zip file are many plethora, potpourri, entourage, myriad of AIS burst IQ files that you can import into Universal Radio Hacker in order to follow along with the rest of this. That said, let me come back over to here. We've opened up the signal in the analysis mode, and here is our raw bit stream. Next thing that we're going to be doing is there any type of line encoding? And inside of the specification, it says, yes, there is. The data encoding says it's NRZI waveform is used for data encoding. Now, this is on the transmitter side. NRZI, it stands for non-return to zero inverted. That's just another way of saying differential. Differential means that you're not looking at the absolute levels. So let me come back over here into this mode. You're not looking at the absolute levels as either 1 or 0. You're looking for the transitions, meaning that typically, they use a transition going from high to low or low to high as a 1 and no transition as a 0. NRZI is a generic term just meaning that you're looking at the transitions, but it doesn't tell you whether or not the transition refers to a 1 or a 0. Therefore, they have to add that information in, which they do. They say the waveform is specified as giving a change in the level when a 0 is encountered. What that means is that you get, when you have a transition in the waveform, that means a 0. No transition is a 1. Come back over to here, into the analysis mode. We need a way to strip off this encoding. To do that, we're going to come over here on the left to where it says decoding. It says non-return to zero NRZ. We're going to click on that, and at the very bottom, there's those 3 dots, the ellipsis. We're going to click on that. It's going to open up this window. As I said, NRZI just means differential encoding. So we're going to click on differential encoding. We're going to click and drag it over to this decoding box. That gets us our differential. The problem is the default for most systems is that when you say differential encoding, they mean a transition is a 1, no transition is a 0. We want the opposite of that. To get that, we're just going to add the invert underneath the differential encoding. So now we have differential encoding and invert. That will give us our NRZI for AIS. The other term that this is typically called is NRZS, standing non-return to zero space. That means that you have a differential encoding in which the transition means a 0. The other one would be NRZM, non-return to 0 mark, meaning a transition refers to a 1. I'm now going to click on Save As, and in the name, I'm going to call it AIS. Click OK. Click Close here. And then now I come over here to my decoding. I click on the down arrow, and there it is. I'm going to click on AIS, and I now have my decoded bit stream that's now going to get me one step closer to accessing the bits, the actual data. To understand the next steps in the decoding, I've come back over to the specification. Specifically, we're looking at a table that provides a summary of the transmission packet. I'm going to start by looking at the first thing that we're going to be looking for, which is a training sequence, which is a 24-bit pattern. Let me come back up here. The training sequence is nothing more than a 1010 pattern, what we call revs or reversals. It's just, again, just a 1010 pattern. And the system specifically states that it doesn't matter whether you start with a 0 or a 1, just so long as 24 times you go from 1 to 0 or 0 to a 1. That's the first thing that we're going to be looking for. Right after that, it says that we have an 8-bit start flag. The 8-bit start flag is stated up here as to be an 8-bit, which is a 0 followed by 6 ones followed by another 0. After that, we actually get into data. A typical packet is 168 bits of data, followed by 16-bit frame check sequence, FCS, which is a cyclic redundancy check, a CRC, that's appended to the data. So that's going to be 16 bits, which means all told, we've got 168 plus 16, which is 184 bits, followed by an end flag, which is identical to the start flag, so looking for another 0, 6 ones, and a 0, and then we're done. Coming back over to Universal Radio Hacker, let's take a look to see if we can identify these components that we've just walked through in the specification. To start with, let's look at, here is our 1010. This is our preamble, the training sequence. And in this particular case, it says that I selected 24, so there is our 24 bits of the training sequence. And that is followed by our start flag. That's a 0 followed by 6 ones, followed by another 0. And if I come up here and I go 0, 1, 2, 3, 4, 5, 6, 0, and I say search, it says that there's 2 of them. Here's the first one, here's the second one. Then in between, we have our data plus our cyclic redundancy check. Therefore, it looks like we've got everything that we need in order to transfer this over to the next component, which is going to be CyberChef. What I'm going to do here is at the little one at the far left end, I'm going to click on that, which is going to highlight all these bits. I'm going to put my cursor over it. I'm going to right click, and I'm going to say copy selection. Bringing up my browser, I'm going to go to CyberChef. Again, I will have a link in the description if you want to follow along. I'm going to right click in here, and I'm going to say paste. And I now have my bits in CyberChef ready to go. Now that I've copied my bitstream into CyberChef, I want to go ahead and get rid of the start flag, the stop flag, the preamble, and all the stuff that comes both before and after those two things. I could have done this just by selecting the appropriate bits in Universal Radio Hacker. This is a personal preference. I just prefer to copy everything into CyberChef and do it there. First thing I'm going to do is I'm going to get rid of the end flag and everything past it. So here is my end flag. Again, it's a 0 followed by 6 ones followed by another 0. I'm going to highlight at the beginning of it and then go all the way to the end and then just hit delete. I'm going to do the same thing with the start flag, except I'm going to start at the end of the start flag and go past it to everything to the beginning. So I now have all these random bits, the training sequence, those 1-0 reversals, followed by the start flag itself, and then just hit delete. I'm left with 185 bits. This is a combination of data, CRC, and something called bit stuffing. How do you know if bit stuffing occurred? And first off, what is bit stuffing? Bit stuffing refers to the fact that in the data, you might have a 0 followed by 6 ones followed by a 0, which would screw up the system because it would recognize that to be either a start flag or an end flag. It would get confused. To prevent that from happening, what they do is before the data goes into the part of the system that adds the start flag, the end flag, the training sequence, and so on, they do something called bit stuffing, meaning it will find any sequence of 5 ones and put a 0 after it. Regardless if that original data was only 5 ones followed by a 0, if you have 5 ones, another 0 gets appended to the rear of it. So looking here, here's 5 ones, and I have a 0 right after it. I'm going to take that 0, and I'm going to get rid of it. That leaves me with 184 bits. 184 is evenly divisible by 8. The AIS format is byte-oriented, meaning that your final data plus your CRC has to be a multiple of 8 bits. 184 is a multiple of 8 bits. Anything around that, well, then you need to get it to a multiple of 8 bits. Most common values that you will see are things such as 184, 440, 176, things such as that. Again, multiple of 8 bits. How many bit stuffings can occur? According to the specification, the vast majority will be 4 or less. However, I have found one burst that had 5 bit stuffings occur. I've actually included it in that zip file that you can find on my GitHub. Now that I have my 184 bits, it's going to be 168 is the actual data, and then the final 16, these bits here, are my frame check sequence or the CRC, whatever you want to call it. It's now time for the CRC check. In CyberChef, to do the CRC check, first thing we're going to add is we're going to add in a block called from binary. Do that in the search. I just typed in binary, and I'm looking for from binary. I'm going to click and drag it over to our recipe. Going to give you a string of random seeming symbols. Ignore that. Next thing, in the search bar, I'm going to type CRC, and I'm looking for the block called CRC checksum. Click and drag that over to our recipe. The algorithm defaults to custom, at least on mine. Perhaps it does something else for yours. I'm going to click on the algorithm, and I'm going to scroll down, and the one that I am looking for is CRC-16/Genibus. Again, CRC-16/Genibus. Click on that. This is what I'm looking for. I've discovered that with AIS signals, if you have a legitimate signal and you're running the appropriate CRC checksum, which this is, with the CRC included, you're going to wind up with E2F0. For those of you who've dealt with CRCs, you might be thinking, well, wait, that's not how it works. Instead, what you should be looking at is, does the CRC of the data match these final 16 bits? Okay. Let me divide these up so that I can create hex characters. This is an E, B, 1, 6. Meaning that if I delete these final 16 bits, this should say EB16 because it will only be operating on the actual data itself. So let's see what happens. Go ahead and delete, highlight those, delete, and there it is. It's EB16. What this means is either way, the data passes the CRC check. That means that you've got good data. The way that the AIS system works, if you do not have a good data set, in other words, if it does not pass CRC, it just throws all of it, it just throws that transmission away. It ignores it completely. Doesn't try to do anything with it. There is no forward error correction. There is nothing, no other mechanism other than to throw it away and just wait for the next one to come in. CRC is a whole topic in and of itself. I'm not going to go any further into it than this, other than to say, in this particular case, the data passes CRC check. This next part is the part that I understand the least. Let me see if I can explain. The way that the data is actually transmitted on a byte level is reversed from normal. If you look at the specification, here in the specification, I'm looking at 1371-6 by the way, it says that character strings are presented left to right, most significant bit first. That's the standard way most people transmit data. However, when they actually transmit it, so when data is output on the VHF data link, each byte should be output with least significant bit first. In other words, if we come back here and we look at our data, every 8 bits has been reversed. In other words, this here on the right is the most significant bit. This bit here on the left is the least significant bit. To better understand that, let me come over here and add another binary, and we're going to go from binary to binary. I'm like, why are you doing that? Reason being is that it really nicely groups everything into 8 bits. Each one of these is transmitted such, again, that the one here on the right is the most significant bit. The one here on the left is the least significant bit. In order to do further processing, we have to swap those around. Unfortunately, there's no easy or good way of doing this. Therefore, I'm going to bite the bullet and I'm going to do this manually. I'm going to highlight this, click copy, and then I'm just going to bring in Notepad, paste these into here, and then I am just going to start manually reversing each one of these. This is the fun part. And there it is. That is, each one of the bytes has now been reversed so that we're back to our original most significant bit first data. I'm going to take this, I'm going to copy it, come back over here, and I'm just going to paste this in here. I now just want to look at each one of these without all of the spaces, because some of the data is going to be less than 8 bits, some is going to be much more than 8 bits. Therefore, let's just get rid of all of the spaces. To do that, I'm going to just come on over here and say remove white space. Come down here, copy. Rid of this, paste. I am now down to my actual, oh my gosh, we finally arrived, data. It's now time to read the data. There are upwards of 20-some different messages that can be sent currently. Regardless of the message though, the first 38 bits are going to be the same. The first 6 bits tells you the message type. To better read this, I'm going to add in a recipe. So first from binary, then to decimal. And since I want to know what the first 6 bits, no, I can already read it, but just in case you can't, this is a message type 1. I'm going to come over here to the U.S. Coast Guard Navigation Center, which nicely lists them all out. You can also find them in the original specification. I just find this easier. Again, link in the description. Number 1 is position report. Click on that. This will allow us to start going through this message to figure out what everything means. I'm going to start with the message ID. I've already identified that. Once I've identified it, I'm just going to start deleting it as we go through. The next 2 bits are a repeat indicator. Just tells you how many times it's been repeated. Most of the time, that's just going to be 0. Come back over here. Next 2 bits, well, it's 0. Okay, get rid of that. The next 30 bits is your MMSI. That is your Maritime Mobile service identity. Think of that as like the serial number for your AIS transmitter. Come over here. I'm going to highlight 30 bits. That is my MMSI in binary. To see it in decimal, I'm going to come down here and I'm going to say 30. The system is not going to be happy about this. CyberChef does not like to deal with this. Regardless, it will still work because down here it says data is not valid byte array. I don't care about that. What I care about is this number right here, 367472930. That is the MMSI for this particular system. I'm going to highlight that. I'm going to right click and say copy. And then I'm going to come over here to marinetraffic.com and I'm going to click at the little window at the top that says search. I'm going to right click in here. I'm going to say paste. And it's going to give me, after a moment, it says, here is the information for this particular transmitter. When I come in and look, guess what? I have found a tugboat. That's pretty cool. I've now identified the MMSI for this particular transmitter. What that means is I can now take those 30 bits and I can say, okay, thank you, your job is done. Just to keep everything clear, I'm going to go ahead and keep a running tally. So message type 1, repeat 0, MMSI. What's next? After the MMSI, I have the navigational status. That is 4 bits. 4 bits is a 12. What does a 12 mean? If I read through this, it says 12 is power-driven vessel pushing ahead or towing alongside. It's a tugboat. It's probably pushing a barge. Something that you would most likely see, especially around the Chesapeake Bay and actually a lot of rivers and everything. Okay, those 4 bits are done. Go ahead and add that. What's next? Rate of turn. That's 8 bits. Here's the thing that you have to understand about most of the AIS messages. Most of the AIS messages use in certain cases they use 2's complement, meaning that the very first bit is a sign bit. If it's a 1, that means it's a negative number. If I do 8 bits here, there I've got 8 selected. If I do 8 here, it says the value is 128. No, if I click down here and say support signed values, that's minus 128. That's actually what I'm looking for. Minus 128 in here means that no turn information available, meaning it's probably just not turning, it's going straight. So rate of turn, not available, minus 28. Another way that you can identify that is it says it's 80 hex, which this value right here is 80 hex. So that would be another way to help you identify that. Get rid of those. What's next? Speed over the ground. That's 10 bits in tenth of knot steps. Let's come over here, say 10. Says it's 74, which means it's in tenths of a knot, divide by 10, so it's 7.4 knots. That's its speed over the ground. Speed over the ground, 7.4 knots. And I can now get rid of those 10 bits. What's next? Position accuracy. 1 bit. 1 is a high, 0 is a low. This one is a 1, which means it's high, which, hey, if you're a tugboat pushing a big barge, in a large body of water, it'd be a good idea for people to know who you are because they don't want to run into you. Go ahead and get rid of that. Add that to my What's next? Longitude, 28 bits. This is also in 2's complement. As it says right here, as per 2's complement. That means I'm looking at that first bit as actually being a sign. Unfortunately, when you get beyond 8 bits, CyberChef does not handle 2's complement, does not handle signed bits well. If I put in 28, it's going to give me a positive number. This is where your calculator or your MATLAB or your GNU Octave is going to come in handy. I'm going to highlight this value. I'm going to right click. I'm going to say copy. I'm going to come down here. I'm going to click paste. And then I'm going to say minus 2 to the 28th to put this actually into a 2's complement value. This is my actual value right here. Minus 458688681. This is in 10,000ths of an arc minute. There are 60 minutes in a degree. In order to get the actual decimal degree value, I'm going to take answer, divide by 10,000, since it's in 10,000ths of an arc minute, and then divide by 60 because there's 60 minutes to a degree. This is my actual value right here. This tugboat was at minus 76.4478 degrees longitude. That means east-west. Negative value means it is west of the prime meridian going through Greenwich. The next part, now that we've got that, I'm going to go ahead and highlight those 28 bits and say you're done. Let me go ahead and also get that into my click copy, longitude, and then I'm going to set up for the latitude. Because the next one is latitude, but it's only 27 bits. I'm going to take this and say 27. Notice that that first bit is a 0, which means it's positive. I don't need to do the subtract 2 to the 27th in this particular case. I've got 235.09792. I'm going to copy that. Once again, you can do this with your calculator. I'm using GNU Octave. Paste. Again, I don't need to do the subtract 2 to the 27th in this case. I just need to divide by 10,000 and then divide by 60. I'm just going to combine that into 1. That is the same as dividing by 600,000. My latitude is 39.18298.7 or 2986, blah, 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 blah. Copy. There, I now have my longitude and latitude for this particular tugboat. We can actually look at this. Move this off to the side so I can see it at least. And I'm going to view on live map. It even tells me where the boat is currently. Isn't that nice? It's way down here in Newport News. I'm going to come up here because I looked at this yesterday. Where the boat was yesterday, and I'm looking down here in the lower right hand corner for these values, the boat was roughly in this area right here, which makes sense because at the time that I collected this signal, I was right about here. So it's a fairly short distance and it's almost directly across water in order to see where the boat was. What's next? We've got those 27 bits taken care of. Let me highlight that. Delete. Next in our report is 12 bits for a course over the ground in 1/10 of a degree. 12 bits. Come down here, say 12, and it says it's 1110, which means it's 111.0. Course over ground, 111.0. Which means, if I look at this here, 111.0 is roughly in this direction here. It's going east-southeast. So it's going this here, and it's going in this direction. Those 12 bits are done. What's next? True heading, 9 bits. It also says 511 indicates not available. 9 bits is 511, which means not available. You can go ahead and get rid of those bits. We're now down to the last 31 bits. Making pretty good headway through this whole thing. Next one, 6 bits, timestamp. Nine. What that means is that this particular signal went out at second 9 after the beginning of the minute. So whatever minute it is, plus 9 seconds, that's when this went out. So timestamp 9. Okay, those 6 bits are done. What is next? 2 bits special maneuver. Okay, 2 bits is just, it's 0, which means not available. Special man 0. Not available. Hang on, rented fingers. That's done. Spare 3 bits. That just means take those 3 bits and get rid of them. You can ignore them. The RAIM flag. I have no idea what that is, but it's either a 0 or a 1. 0 is not in use. 1 is in use. It's a 0, so it's not in use. And I'm left with my final 19 bits, which is a communication state. For this one, I'm going to bring back here, and I'm going to look for my communication state. I'm actually looking for table 18 and 19. Here. What I'm looking for with these 19 bits, the first 2 bits is my sync state. First 2 bits is are 0, 0, meaning it's a 0. Let me go ahead and get rid of that. I'm going to look at what that means. 0 is UTC direct. Okay. The next one, whoops. Too many things going on at once. Next 3 bits is my slot time out. Next 3 bits is just a 1. So that's 1. What does that mean? 1 means that 1 to 7 frames respectively are left until slot change. And then finally I've got 14 bits for a sub message, which depends on the current value in the slot timeout. Come down here. 1 means that the rest is a UTC hour and minute. This is a bits 13 to 9, and this is 0 indexed. 1329 are the hour. The minute is bits 8 through 2. In other words, this is the first 5 bits. This is 8, 7, 6, 5, 4, 3, 2, 7 bits, and then the last 2 bits are ignored. So it's 5 and 7. Come over here, we're going to say, what is 5? 5 means its hour is 16 in Universal Coordinated Time. That's 4 o'clock in the afternoon. And again, that's UTC, and we are, I think at the time we were 4 hours behind, so this would have been about noon. So it's either 12 or 11 local time. I'd have to go back and take a look. We're done with those 5 bits for the 16. Let me highlight those and delete them. We're left with the last 7 bits, which says that those 7 bits are a 26, meaning that our time locally was 1626, or actually 1626 Universal Coordinated Time, which, like I said, is either going to be 11 or noon. So 11:26 or 12:26 local time, depending on when this, whether we're under daylight savings times or not. And honestly, I can't remember. I have to go back and look. Regardless, we've now gone through, because those last 2 bits we can ignore. We've now gone through every single bit of the message. We are done. This wraps up how to go through a AIS message from start to finish, how to capture it, how to demodulate it, how to decode it. This is longer than I normally like my videos to be, but I thought it was important to actually walk it from one end to the other. I hope you appreciated this video. If so, go ahead and smash the like button in the description, and I will see you all next time.